Hello, warm welcome back. Good to have everyone here for the second half of the AP Calc AB FRQ Standards Practice. Now, this series, 6-part series, covers 3 non-calculated problems, which we've completed already. So go check those out if you want to, acquire some more techniques before you come to these calculated problems. So that is what we're starting with today. Get yourself ready with a notebook, grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have this calculator problem. Again, these are all provided from the University of Houston. Thanks to the University of Houston, who clearly wants you all succeeding on your AP Calculus exams with this generous practice. Now, a little bit of a disclaimer. These problems are not extremely difficult, so I wouldn't say that they are, in terms of difficulty, a full representation, 100% representation of the AP exam, but the questions that they're asking you, those are the types of questions they'll be asking you, just with probably some tougher situations. Now, that being said, we're doing the calculator section, so we have Desmos to help us out, and that's going to make things very, very easy and effortless. So we're just going to focus on setting things up. That's why this is the standards practice, not any intense AB session or run through of actual AP problems, but just kind of a loose simulation, right? I don't want you to see this problem and expect that you've done a harder question than anything you should expect on the AP exam. No, you should still expect harder questions on the AP exam. It's just that here we're just following the techniques and getting a feel for the processes. So go ahead and give yourself about 12 minutes or so to work this out. Pause the video, whatever you need to do. Or you can run through it in real time if you'd like. Try to do a side-by-side if you can keep up. That's fine. Either way, when you're ready, you come back, see how we did it here. And here we go. We're given a region in the first quadrant bounded by the graphs of e to the negative x squared and 4x squared. Now, even without a calculator, and the y-axis, even without a calculator, you should know roughly what that looks like. So this is first quadrant. E to the negative x squared is going to make this kind of like bell curve shape on both sides. It should be symmetric. I know I'm not drawing it perfectly symmetrically, but it should be symmetric. Wow, pretty bad symmetry today, huh? Yeah, that's a little better. And 4x squared, of course, is just a parabola, but a really steep one. And we're focusing on the part in the first quadrant. So you can graph that if you'd like to on Desmos, but I don't think we really need the graphing software for that part necessarily. And that being said, you'll notice that we're going to find the area of this region. So part A says find the area. And of course, we're going to use an integral for that. Now, it's pretty simple to do this dx, top function minus bottom function, from 0 to wherever this point is located. So using Desmos, it's pretty easy to find out where that point is located. I generally prefer to subtract these two and find where their difference equals 0. So I'm going to do that. I'll show you how I do that. So I could graph e to the negative x squared, see that bell curve, and I could graph y equals 4x squared. And I could see where they cross, and that's great, 0.45151. What I prefer to do sometimes is I prefer to subtract the two. And then you still get the same x value, but it's at a 0. So literally the difference is 0. They have no difference. And if they have no difference, they are the same. They're equal in value. So this happens at 0.45154, which means we're going to need to set up an integral from 0 to 0.45154. Up top function minus bottom function, which you'll notice I kind of already did, e to the negative x squared minus 4x squared. And in Desmos, we're going to have to use parentheses on the integrand, always. So let's go ahead and calculate that. Integral from 0 to 0.45154 of parentheses e to the negative x squared minus 4x squared dx. And There you have it. Pretty easy. 0.299889, close enough to 0.300, though we're just going to round this. This is approximately 0.300. Okay, very easy to set up this integral. We're integrating dx, which basically means we're taking a bunch of vertical strips, thin vertical strips, and we're adding all of these strips up. And the strip length is top function minus bottom function. So if we add those all up with an integral, we get the area of the region. Okay, great. Let's move on to part B. Find the volume of the solid generated when S is rotated about the x-axis. Okay, so I'm going to redraw this region, actually. I'm going to sketch it because we're going around the x-axis, which is going to incur the washer method. Why is it going to be a washer? Well, the x-axis is not one of the boundaries of the region. So our rotations are going to look something like this. Here's just the first quadrant. We'll have something like that, and we'll have something like that. But we'll exaggerate it a little bit. We'll make it go like that and like that. Okay, now if we three-dimensionalize this a little bit, I'll do my best. And we rotate this around the x-axis, which is this axis, you're going to see that each one of these slices has a rotation from the outer, and then it has a rotation from the inner. So each one of these slices is basically a circle, but with a little hole inside of it, right? So here is the diagram for each one of those slices, with the x-axis being the center of the slice. We have this little tiny r value, and then we have this bigger r value. Okay, so the area that we're considering for each of the slices is the area between these regions. That's going to be with a radius of e to the negative x squared, and little r is going to be the radius of 4x squared. So the area of each one of these slices is big circle minus little circle, pi r squared, rather pi big R squared minus pi little r squared. So I'll write it like this with the pi factored out. And then we just have to, well, I won't get too hasty. Then we just have to put this in the power. So if I square this, I could call it negative 2x squared, or I could call it negative x squared all squared. Doesn't really matter too much. I'm just going to be succinct. I'm going to put it in here just because it's a little bit faster. And then we have minus 4x squared squared. Of course, that's just 16x to the fourth. Okay, so let's put that in an integral because that's going to give us our volume. And we're going from the same limits of integration. So really all I have to do to modify this is put a pi there, put a 2 there, turn this into a 16, and turn this into a 4. And that gives me the same thing as if I had put this in parentheses and squared it. And if I had put 4x squared in parentheses and squared it, same thing, right? 1.059 basically. So that was 1.059. This is also 1.059. So nothing changes there. In fact, I think I'll take this entire, I think I'll take this entire little snippet. This is what I would write down by hand, of course, but since we're on the computer, we might as well take that. And so this is going to be 1.059. Okay, yeah, making light work of this, quick work of this. Part C says if the region S is the base of a solid for which each cross-section perpendicular to the x-axis is an equilateral triangle, find the volume of the solid. So we're going to represent the region one more time. And what we have instead here is we have that we're creating these, again, I'll try to three-dimensionalize it simply, but as best as possible, let's try to make those almost connect. That's better. If we three-dimensionalize this as best as possible, then what it's saying is that we're going to have these equilateral triangles with a base. One of the sides is this in this region. So there's an equilateral triangle that sticks out. And then at other x values, like at this x value here, we're going to have a slightly bigger equilateral triangle that sticks out. And it's bigger because the distance between these two is bigger, so that base is bigger. The biggest equilateral triangle is going to be at x equals 0, which is just going to go right along that wall there. Okay, so what we want to do is we want to represent the area of these equilateral triangles, and then we want to add them all up. So this is equal to top function minus bottom function minus 4x squared. But we're just going to call it S for now. So in general, you should remember this from geometry, but in case you don't, when we have an equilateral triangle, we can kind of like split it down the middle, and that would turn it into a 30, 60, 90 triangle, where we'll split it into two 30, 60, 90 triangles, where the base is now S over 2, which means this is S, right? It's a side length. And this is S root 3 over 2. Maybe we'll call it root 3S over 2. And you can see that with some simple geometry, do some SOHCAHTOA business. Well, that means that this height is therefore root 3 over 2 times e to the negative x squared minus 4x squared. Which is kind of messy, but all you have to do is think about it like this. We have 1/2 base, which is s, times height, which is root 3 over 2s. Altogether, that gives us root 3 over 4s squared, and then we can simply plug that in parentheses. We're not going to do anything fancy with it. We're just going to plug it in. Okay, that's the area of one of these triangles. And if we want to get the volume of the solid that will be created, it's going to be like this series of equilateral triangles, that are basically getting smaller and smaller as we go down. In order to add them all up, we use an integral. So that is guiding us through this whole process. We need to find the area of the cross-sectional slices. There's no pi in this one. Find the area of the cross-sectional slices, whether it be a washer, whether it be a triangle, and you add them all up. So from 0 to 0.45154, and then this thing's squared. Sorry guys, I forgot that. So it's not the same as each one of them squared. It's the entire quantity squared. That is very different. All right, let's see what that comes out to be on Desmos. We already have most of our stuff here. Let's turn this into a square root of 3 or 4. And then instead of having these be squared, so turn this back to a 4x squared, this whole thing is going to be squared. There we go. Surprisingly, very small area. I guess that makes sense because we're not revolving it, so it's just like within this region, basically. Okay, so we get 0.104. That's how it rounds, right? That's how we round it there. So 0.104. Considering that the other one was like 1.059, that's not too surprising. Let's just make sure this integrator is good again. Oops. So this is going to be e to the negative x squared minus 4x squared, and then that squared. Yep, 0.104. So this was a perfect question for practicing how do we set up integral to find us either the area or find us the volume with these washers. Remember why we used washers? Because the boundary that the line that we rotated around was not one of the boundaries of the region. And then we turned the region into the base with some solids, with some equilateral triangles sticking out from that. And so if we can find the area of the cross-section in terms of the functions, you're 60% of the way there. You just got to slap it into an integral, especially on Desmos with a calculator, and make sure you type things in carefully, because if you can't check it mathematically, like, to be honest, I wouldn't be able to just whip that up by hand and be like, oh yeah, sure, that seems reasonable. I got to just trust my input and very carefully use my eyes. Otherwise, possibly doing it wrong. Okay? So, that's a blab out of me. Stick with us for the next couple of videos in the series to round out the AP Calc FRQ standards. And I'll see you next time in the void.